Antimatter is matter moving backwards in time, according to Richard Feynman. So, what is antimatter? In 1928, Paul Dirac came out with an elegant equation, another version of Schrödinger's equation, to describe how particles like electrons behave when they travel close to the speed of light. His experiment had two solutions. The first solution described an electron, and the second solution described an anti-electron. Calculating work. This electron would have the same properties of an electron, but it would have an opposite charge. Pair production, which is the opposite of annihilation, occurs when bosons, example photons, of high energy create matter and antimatter, like an electron and a positron. The photon's energy is converted into mass according to Einstein's equation E equals mc squared. In 1932, Carl Anderson observed particles racing through a bubble chamber. His measurements of these particles showed that they had the same mass as that of the electron, but with positive electric charge. This was the first detection of antimatter. There is this kind of asymmetry between matter and antimatter. Neutrinos could be the reason the Big Bang didn't consume us completely. They are particles and antiparticles of their own, and they are the only fundamental particles with this property. There are three different flavors of neutrinos if you have it, and these have a mixture of their properties. And so, when experimentalists are trying to observe the property and difference between these particles, they, in different times, depict different properties. Thus, as they approach, they change their inherent behaviors. Antiparticles are created everywhere in the universe where high energy particle collisions take place. High energy cosmic rays striking Earth's atmosphere produce minute quantities of antiparticles. Antimatter may exist in relatively large amounts in faraway galaxies due to cosmic inflation in the primordial time of the universe. During the Big Bang, there were equal amounts of matter and antimatter created. So why are all these not colliding and annihilating? One of the ways to describe the imbalance in the amount of matter to antimatter is the weak nuclear force. Scientists in 1980 used neutral kaons, which are made up of quarks, one having a down quark bound to anti-strange quark and the other strange quark bound to anti-down quark. But these two do not annihilate together, even though they had directly opposite constituents. It all boiled down to how they each decayed. CPT symmetry is able to describe baryonic matter, the matter we are all made up of. There are three fundamental symmetries in physics, and they are charge, parity, and time. Charge symmetry means if you flip the charges of all particles involved in a reaction, it will result in the same reaction. Parity is the idea that if you look at the mirror of an interaction, you will have the same results. Time symmetry means that if you run an interaction backward in time, it will result in the same thing, and this is called the CPT symmetry for charge, parity, and time. The Sakharov condition is what is responsible for baryogenesis to occur. In fact, this scientist Sakharov kept some conditions down to be able to describe the possibility of the imbalance of matter and antimatter. The first one is the violation of the CP symmetry, and we have seen this to be true because weak nuclear force breaks this symmetry. Weak nuclear forces allows for CP symmetry to be obsolete. Different temperatures in different places, that is how the universe is out of equilibrium. And we observe this because of entropy. The universe is not in equilibrium as it continues to expand almost all the time. Baryon number violation. In nature, if you have a baryon and it decays, a baryon is produced. No more, no less. That means baryon number is always conserved. This third condition not being met makes our question begging to be answered still. Well, maybe there is a different dimension of physics that would explain how this antimatter is so small in amount as compared to matter. Maybe they banged in the opposite direction with respect to matter, or maybe we should be leaving it to the upcoming grand unified theory when it shows up. But until then, we stick with these theories of why we are here and why we exist anyway. Thank you so much for watching. There's Einstein in a flash. Until next time, goodbye.